today's talk, I'm going to give you some background as to what we do as a company and the problems we run into. Then I'm going to tell you what inspired us to get to our solution. And finally, I'm going to show you some awesome stuff. So I've been told by the powers that be that I have to sex up this talk. Now, I don't want to stand in my underwear, so I'm going to show you some nerdy stuff which all of you will appreciate. Okay, cool. So some background. I work for Intellection Software. We have a product called Inside Out. It's a software as a service market research platform. Okay, so it needs real-time statistics on highly dimensional data, and it needs to be pretty fast. The problem is that Ruby is pretty slow. Okay. So yeah, Ruby is slow, and there are no real good tools for data analysis in Ruby. There's an array, and I think that's about it. So we started looking for a solution, and as has been mentioned a few times in this conference already, there's pandas, which is pretty cool. There's also NumPy, all kinds of other stuff because, well, Python has been adopted so widely in the scientific community. So we have all of these great tools in Python. Okay. But the problem is we can't rewrite all of our code in Python. We have tons of Ruby code, and we have tons of Ruby developers, so we just can't lose all that experience. So basically what we want to do is we want to write Ruby, use Ruby as a modeling language, but execute Python. So how do we do this? Okay. So just going back a bit, let me start off by showing you what we have, and then I'll show you how we went there to do it. Of course, I'm going to switch to a notebook. This guy you've seen before. So it's just a basic pandas data frame, some metadata, and some basic, yeah, we can get a column from this data frame, and we can do a meme. This is all old news to everyone. You can also create a series from that, select a column, and we can do some other operations, a group by, and some, well, whatever we fancy. Cool. So we came across this cool thing called the iRuby notebook, which is basically the IPython notebook but sitting on a Ruby kernel. And it is pretty cool. So let me show you what we've done. We have kind of mirrored exactly what pandas does, but in Ruby. So for example, we have a Ruby hash, exactly the same as the previous one. And well, we just call our data frame a measure table. And yeah, sorry. As you can see, we get exactly the same results. And just so you see I'm not lying, I'm going to execute this again. And there we go. Cool. We can do the same. We can do a mean. We can get a series out. And we can do all of our math. Exactly the same as in pandas. Yeah, cool. So there we go. Okay, so back to the talk. There it is. Okay, so how do we do this? Well, what we do is we build up an expression tree in Ruby. We then send that tree to a cluster of Python workers. Then we mangle and rewrite those trees so that Python can understand them. We also do some optimization. Then we execute the tree in Python, and then we return the result to Ruby. Okay, cool. So, well, how do we come to the solution? Well, firstly, we looked at tools we use every day. Well, all of you have, well, most of you have used Django before. In the Ruby world, we use Rails. And the really cool thing about this is the Django's models. So we can have a coffee beans model, and we can do a filter on it by country. We can also exclude some stuff, and we can do order whatever we want. The cool thing about this is nothing gets executed until we do this. So everything is deferred until we want the final answer. And now this is pretty cool, especially for the modeling, the market research world as well, where you have huge data sets coming in, but the final answer is really small, and you don't want this to be executed every time for every step. Okay, so how does, okay, and yeah, this is the query that gets built up from this model. Cool. So how does it work? Well, internally, Django's ORM builds up expression trees for these what I call these models that get chained together to get a final result. So for example, our first one, we can see there's a query operator, where operator, and where equals country of origin is Kenya. Okay. Then it changes a bit when we add more to it. Now there's an AND operator again, and yeah, star country of origin and just the way roast is not equal to dark. And when we order, it just kind of changes this expression tree and finally builds up the query. Cool. Now, the thing is, this is all okay and well, but how do we send this over the wire, and how do we change it, and how do we mangle it to do what we want with it? And that is what led us to our second piece of inspiration, which is Lisp. Okay. Now, yeah, you'll notice if you look at Lisp code, there's a lot of parentheses, and it is because Lisp stands for list processing. Okay. Lisp has this amazing property called homoiconicity, which basically means that it treats code exactly the same as it treats its data structure. So basically, code is data. So having a look at the textbook example, of the textbook definition of homoiconicity, it means that languages in which program code is represented as a language fundamental data type are called homoiconic. Okay. Now, this is pretty powerful. It may not be apparent yet, but we'll get there. Cool. So I'm going to briefly introduce you to two core concepts of Lisp. First, S expressions, and then going on to the list. So S expressions stand for symbolic expression. The first element is an operator or method, function, whatever you like. All remaining elements are data. S expressions can be nested, and every element can be replaced with the value it evaluates to. All right, so let's write an S expression for 1 plus 18. It will look something like this. First element is an operator, and the remaining elements are the data. They can be nested, so instead of 18, we can have 3 multiplied by 6. And again, we can replace every expression with the value it evaluates to. Now let's have a look at lists. Lists in Lisp are singly linked. They're built up from this thing called a console, which I'll talk about a bit later. They are null terminated, and we create them using the list operator. Char is a method which returns the first element of a console. I'm going to call it head because char is confusing. Coda returns the rest of it. I'm going to call it tail because coda is confusing. And then last returns the last console in a list. Okay. So let's have a look. This is basically a list in Lisp, first 4 Fibonacci numbers. Thing is, if I try to run this in a Lisp REPL, I get an error, illegal function call. Because Lisp thinks that this is a S expression, and there is no function named 1, so it doesn't know what to do, and it dies. So the problem, or the way to get around it, is to use the list operator, and this will work. You can also use quote, which is pretty powerful. Quote tells Lisp not to execute whatever is following. So this also works, and I like quote, so I'm going to use it throughout. Okay. This is a representation of how lists look internally in Lisp. So that first block is a console with the data and the next element in a console pointing to the next, and so on until you get to null. Okay. So if we do head of this list, we get 1. Okay. If we do tail, we get the rest, which is this. And if we do last, we get the last console, which is that. Cool. Now back to homoiconicity. So let's start with a list of Fibonacci numbers. The last one is wrong. We want to change it. Cool. So what we do is we can set it to variable A. Then we can get the last element. So last returns to the last console. We actually want to get to that element. So that's why we use head of the last console, and that gives us the 26. And now we can set that to a variable, or we can set that to 25. Okay, yeah, but so what? We've changed the list. It's not really that amazing. The cool thing is that Lisp handles code exactly the same as data. So we can do exactly this with some code. So let's look at a trivial example, expression of 1 plus 2. This can be much more complicated, but for the sake of brevity, I'm going to keep it to this. We can set that piece of code to a variable. If we eval it, we get the answer. And now we can change it. We can say, well, I want it to be 1 plus 3. And then if we eval it again, we get 4. Okay. So it might not be so apparent now, but it's really powerful. It's mind-blowing, in fact. So I'd urge you all to take a weekend, go find an ebook on the internet and read up on this. Your life will never be the same again. Cool. Okay. This reminds me of this beautiful sketch by Eschke. You know, the drawing hands, kind of something that changes itself, why it's going on. And Mr. Douglas Hofstadter has this really cool quote about Lisp. You know, he's kind of the definitive author on Eschke and Gödel and Bach and all those amazing people. Yeah, and he praises Lisp. So if he thinks it's cool, yeah, it's pretty cool. Okay. Now finally, some Python. Cool. So let's again look at a simple data frame, and where I just want to name the index. Cool. So in Python, it would look something like this. I create my data frame and I set the name of my index to be index. In Lisp, it will probably look something like this. I will first do a get at. I will get the index attribute of the data frame, and then I will set that attribute on that object, set the attribute name to index name. Okay. The problem is that this evaluates to null because set at doesn't return anything. So chaining becomes a problem. I can't chain the result of this I can't change something else more to the result of this because, yeah, it's pretty obvious. So what do? Well, we tap it. Tap is a pretty cool function. We got inspired from Ruby by it. And basically it takes 2 arguments, or it can, many arguments, and it executes from the second argument onwards, and it returns the first argument. So it basically looks like this in Python. So now we can do this. We can tap our data frame. We can do all of this, and this will return the data frame. Cool. So now we can chain it. The problem is that it's way too much Python. This is pretty complicated for setting the name of an index. We want this, okay? And that is where Lisp's Homer iconicity comes in. We can send this to Python, then rewrite this on the Python side to look like this. So take a moment to think about this. It's pretty trivial, but the things you can do with this is amazing. If you have a huge data frame we have this example, 20,000 columns, and you need to do computations on that. You know, doing it on a single worker will take ages. So on the Python side, when this expression comes in, we can analyze it and we can see, well, we can break this up in chunks, and we can execute these on a bunch of workers. And then finally, we can reduce the result again and return the result to Python. It's pretty amazing. Okay. The next thing is inspectability. So now we're writing Ruby, but executing Python, and there can be all kinds of hell, and you would have no idea what is going on. So we need inspectability, and it's really important to see what is going on the Ruby side and on the Python side. So we are using the iRuby notebook for this and some D3 magic. So let me show you. Okay. So here we have our some computations to get the percent of rainfall in each of these cities. Now I want to see what actually is going on. What am I doing to get to this result? So what I can do is I can ask my notebook to show me the expression. And then we get this. Okay. So this is for the first one. It's just create a new measure table, set the index to country and city, and then get the rainfall column for me. So that's a pretty trivial example. We can do the same with our more complex one, which is this one, the percent rainfall in each city. Okay. So let's ask it to show us the expression. And now you can see this is a bit more complex. So we start off, we create a new measure table, we set our indexes, we do a group by country and city, a group by country, we do a sum on that, we get the rainfall column out, we divide it by the rainfall, and we can set its name, and we can again multiply by 100 to get a percentage. Okay, but again, this is all Ruby. We want to see what happened on the Python side and what happened as we executed this tree. So you can see, for example, this set name, this doesn't exist in Python, it's something else. So let's look at the expression as it got rewritten on the Python side. So for that we can just switch and then it redraws. Let me just show you again because this is the sexed up part. So show you and yeah. So it's pretty cool. So let's see. So what we have is we can have all kinds of things that got all kind of metadata about this tree as it got executed in Python. We can have the execution time of this specific node. We can also have the cumulative time as to how long everything took up to here. And this is pretty powerful. So in one look, we can see where our bottlenecks are and where we can do things to make this faster. So let's go to the correct place, and we did a set index, a reset index, group by, sum, and now you can see here's our set attr and our tap, and our set attr and tap again. And this wasn't visible on the Ruby tree, so we can see how we rewrote it. Okay, that's cool and all if everything works, but what if something breaks? Okay, so let's try to break it. It's just this same expression again, but I am just making a mistake and not spelling rainfall with a capital R. So let's see what happens. So yeah, this is our Ruby expression. It looks pretty much the same. So let's see what happened in Python. So now we can see that there was an issue. We can zoom in. And we can see that there was and this is what I hate so much, every time in Python you see something like that and you don't know what it is, that rainfall string, what does it mean? But, so let's have a look at the traceback. So we can do this by simply hovering over, and then we can have the Python traceback on our tree. And that's pretty cool, I think. Cool. Well, so yeah. Let's have a look. So what do we gain? We can lock down a modeling language in Ruby. This means that as versions of pandas change, we don't need to change any Ruby code. It all stays static. We also don't need to worry about parallelization and into how many workers it gets split up or any of those things. It all gets calculated on the Python side because we rewrite this tree on the Python side. That goes hand in hand with manipulating our code as data. The cool thing as well is we can use other languages. For example, Julia is pretty good at doing stuff in parallel. So we can just write an interpreter in Julia for this tree, send this tree to Julia, and there we have it. None of our modeling language, none of our models change anyhow. Okay. So yeah, a big thank you. I need to thank Intellection for allowing me to come here. Brendan and Tim, my awesome colleagues, who've put up with me and my lack of Ruby knowledge. And then all of you, thanks for coming.